Next, we will discuss about the close packing in 3 dimension. As we know, all crystals are 3-dimensional structures and they can be obtained by stacking 2-dimensional layers one above the other. In the last section, we had discussed about the close packing in 2 dimension, which can be of 2 types, square close packed and hexagonal close packed. Let's see what type of 3-dimensional close packing can be obtained from these. Here, as you can see, the spheres are aligned horizontally as well as vertically. If the arrangement of spheres in the first layer is considered to be of A type, then the arrangement of spheres in the subsequent layers is also of A type. This 3-dimensional arrangement is referred to as the AAA type pattern. And if you look carefully to this, you will find that this arrangement has resulted in the formation of a simple cubic lattice like this. The unit of this lattice is a primitive cubic unit cell. Let's consider another way to build 3-dimensional close packing is from a 2-dimensional hexagonal close packing. As you can see, the depressions of the first layer are the ideal seeds for the next layers of spheres. Let's take a 2-dimensional hexagonal close packed layer A type and place a similar layer above it such that the spheres of the second layer are placed in the depressions of the first layer. Since the spheres of the 2 layers are aligned differently, let us call the second layer as B type. A closer look at the arrangement indicates the formation of 2 different kinds of voids. Do you know what are they? Let's see. They are tetrahedral voids and octahedral voids. Let's discuss them in detail. Tetrahedral voids are formed whenever a sphere of the second layer is above the void of the first layer. Then what about the octahedral voids? We observe that the triangular voids in the second layer are above the triangular voids in the first layer, such that the triangular voids do not overlap. One of them has the apex of the triangle pointing upwards and the other downwards. Such voids are called octahedral voids and they are surrounded by 6 spheres. Friends, do you know we can easily calculate the number of these 2 types of voids? But how? Let's see. Let the number of close packed spheres be n and the number of octahedral voids generated is equal to n and the number of tetrahedral voids generated is equal to 2n. Next, we will study the different ways in which the third layer can be placed over the second layer. There are 2 ways. Let's discuss them in detail. So, the first one is by covering the tetrahedral voids. In this kind of close packing, the spheres of the third layer are exactly aligned with those of the first layer. Thus, if we name the first layer as A and second as B, then the third layer can be again be named as A. This pattern can be written as ABAB pattern and this structure is known as hexagonal close packed structure. This sort of arrangement of atoms can be found in many metals like magnesium and zinc. Now let's discuss about the next way, that is by covering octahedral voids. In this kind of close packing, the spheres of the third layer are not aligned with those of either the first or the second. Thus, if we name the first layer as A and the second layer as B, then the third layer will be named as C. This pattern of layer can be written as ABC type. This crystal structure is called cubic close packed or face centered cubic structure. In both of them, the coordination number is 12 as each sphere is in contact with 12 spheres. Metals like copper and silver crystallize in this structure. In both of them, 74% space in the crystal is filled with these kind of close packing. Moving to the next topic, that is formula of a compound and number of voids filled. Here, the number of octahedral voids present in the lattice is equal to the number of close packed particles, and the number of tetrahedral voids produced is twice this number. In ionic solids, the bigger ions, that is anions, form a close packed structure, and the smaller ions, that is cations, occupy the voids. If the latter ion is small, then tetrahedral voids are occupied, and if the latter ion is bigger, then octahedral voids are occupied. In a compound, the fraction of octahedral and tetrahedral voids that are occupied depends upon the chemical formula of the compound. Close packed structures have both tetrahedral and octahedral voids. Friends, now let's see how we can locate tetrahedral and octahedral voids. So the first one is locating tetrahedral voids. Here, take a unit cell of CCP or FCC lattice divided into 8 small cubes with each small cube having atoms at alternate corners. Thus, each small cube has 4 atoms that on joining to each other make a regular tetrahedron. Thus, there is one tetrahedral void in each small cube and 8 tetrahedral voids in total. Each of the 8 small cubes have one void in one unit cell of CCP. CCP structure has 4 atoms per unit cell. Thus, we can say that the number of tetrahedral voids is twice the number of atoms. Now, let's discuss the second one, that is locating octahedral voids. Take a unit cell of CCP or FCC. The body center of the cube C is not occupied, but surrounded by 6 atoms on face centers. Joining the face centers creates an octahedron. Thus, this unit cell has one octahedral void at the body center of the cube. There is one octahedral void at the center of each of the 12 edges. As you can see, it is surrounded by 6 atoms, 4 belonging to the same unit cell and 2 belonging to 2 adjacent unit cells. Each edge of the cube and octahedral void are shared between 4 adjacent unit cells. So, only 1/4 of each void belongs to a particular unit cell. Thus, in cubic close packed structure, octahedral void at the body center of the cube is equal to 1. 12 octahedral voids located at each edge and shared between 4 unit cells is equal to 12 into 1/4. That is equal to 3. Therefore, total number of octahedral voids is equal to 4. As we know that in CCP structure, each unit cell has 4 atoms. Thus, we can say that the number of octahedral voids is equal to this number. Okay friends, now it is problem time. Let's see. Atom of element B form the HCP lattice and those of element A occupy 2/3 of tetrahedral voids. Then, what is the formula of the compound formed by the elements A and B? Do you have any idea? Well, let's see. The number of tetrahedral voids formed is equal to twice the number of atoms of element B, and only 2/3 of these are occupied by the atoms of element A. Hence, the ratio of number of atoms of A and B is 2 into 2/3 is to 1 or 4 is to 3. And the formula of the compound is A for B3. Next, we will discuss about the packing efficiency. Do you know what is packing efficiency? In whatever the way the constituent particles such as atoms, molecules or ions are packed, there is always some free space in the form of voids. Thus, we can say that packing efficiency is the percentage of total space filled by the particles. Therefore, packing efficiency is equal to volume occupied by 4 spheres in the unit cell divided by total volume of the unit cell into 100%. Let us calculate the packing efficiency of different types of structures. So first, we will calculate the packing efficiency of cubic close packed structure. Here, let us consider the triangle ABC and let the unit cell edge length be small a and face diagonal AC is equal to small b. According to Pythagoras theorem, hypotenuse square is equal to base square plus altitude square. Thus, we can say that AC square is equal to small b square. That is equal to BC square plus AB square. That is equal to small a square plus small a square. That is equal to 2 small a square, or B is equal to root of 2a. Consider this as equation 1. If R is the radius of the sphere, then we find that small b is equal to 4 into small r. Consider this as equation number 2. Equating both the equations, we get 4 into small r is equal to root of 2a, or a is equal to 4r divided by root 2. That is equal to 2 into root of 2r. We can also write that r is equal to a divided by 2 into root 2. We know that each unit cell in CCP structure has effectively 4 spheres. Thus, we can say that total volume of 4 spheres is equal to 4 into 4 by 3 into pi r cube, and volume of the cube is a cube, or 2 into root of 2r the whole cube. Therefore, the packing efficiency is equal to volume occupied by 4 spheres in the unit cell divided by total volume of the unit cell into 100. That is equal to 4 into 4 by 3 pi r cube divided by 2 into root of 2r the whole cube into 100. That is equal to 16 by 3 into pi r cube divided by 16 into root 2 into r cube into 100. That is equal to 74%. Thus, we can say that the packing efficiency of cubic close packed structure is 74%. Now, let's calculate the packing efficiency of body-centered cubic structures. In body-centered cubic unit cell, one atom is present at the body center apart from the corners of the cube. Let us take a unit cell of edge length small a and consider the triangle EFD. In triangle EFD, small b square is equal to small a square plus small a square. That is equal to 2 into small a square. That is, b is equal to root 2 into a. Let us now consider triangle AFD. Length of body diagonal C can be calculated by the help of Pythagoras theorem. That is, small c square is equal to small a square plus b square, where small b is the length of the face diagonal. Thus, small b is equal to root 2 into a. That is, c square is equal to a square plus b square. That is equal to a square plus 2a square. Thus, we can say that C is equal to root 3 into A. Well, the length of the body diagonal C is equal to 4 into small r, where small r is the radius of the sphere as all the three spheres along the diagonal touch each other. Therefore, root 3 into A is equal to 4 into small r, or small a is equal to 4r divided by root 3. Also, we can write small r is equal to root 3 into A divided by 4. In this type of structure, the total number of atoms is 2 and their volume is equal to 2 into 4 by 3 pi r cube. Volume of the cube A cube will be equal to 4 into r divided by root 3 the whole cube, or A cube is equal to 4r divided by root 3 the whole cube. Therefore, the packing efficiency is equal to volume occupied by two spheres in the unit cell divided by total volume of the unit cell into 100. That is equal to 2 into 4 by 3 pi r cube divided by 4r divided by root 3 the whole cube into 100. That is equal to 8 by 3 pi r cube divided by 64 divided by 3 into root 3 into r cube into 100. That is equal to 68%. Thus, we can say that the packing efficiency of body-centered cubic structure is 68%. Next, we will calculate the packing efficiency of simple cubic lattice. In a simple cubic lattice, atoms are only present at the corners of the cube and they touch each other along the edges. Thus, the edge length or side of the cube A and radius of the particles R are related as A is equal to 2R, and the volume of the cubic unit cell is equal to A cube is equal to 2R the whole cube is equal to 8R cube. Since a simple cubic lattice contains only one atom, the volume of the occupied space is equal to 4 by 3 pi r cube. Therefore, the packing efficiency is equal to volume of one atom divided by volume of cubic unit cell into 100. That is equal to 4 by 3 pi r cube divided by 8r cube into 100. That is equal to pi into 100 divided by 6. That is equal to 52.36%. That is approximately equal to 52.4%. Thus, we can say that cubic close-packed structure and hexagonal close-packed structures have maximum packing efficiency. Next, we will discuss the calculations involving unit cell dimensions. The edge length of a cubic crystal of an element is taken as small a. Then the density can be calculated as follows. Density of unit cell small d is equal to mass of unit cell divided by volume of unit cell. In case of cubic crystal, volume of unit cell is equal to small a cube and mass of the unit cell is equal to number of atoms in the unit cell into mass of each atom. That is equal to Z into M. Here, Z is the number of atoms present in one unit cell and small m is the mass of a single atom. Mass of an atom present in the unit cell small m is equal to molar mass divided by Avogadro's number. That is equal to capital M divided by Na. Mass of unit cell is equal to Z into capital M divided by Na. Thus, we can say that density of unit cell small d is equal to Z into small m divided by A cube, or d is equal to Z into capital M divided by Na into A cube. If A is in centimeter and M is in gram, then the density will be in gram per centimeter cube. Okay friends, now it is problem time. Let's go to the first problem. That is, an element has a body-centered cube structure with a cell edge of 288 picometer. The density of the element is 7.2 gram per centimeter cube. Then, how many atoms are present in 208 gram of the element? Do you have any idea? Well, I will tell you. Here, the volume of the unit cell is equal to 288 picometer the whole cube. That is equal to 288 into 10 raised to minus 12 meter the whole cube. That is equal to 288 into 10 raised to minus 10 centimeter the whole cube. That is equal to 2.39 into 10 raised to minus 23 centimeter cube. Then the volume of 208 gram of the element is equal to mass by density. Substituting the values, we get 208 gram divided by 7.2 gram centimeter raised to minus 3 is equal to 28.88 centimeter cube. Then the number of unit cells in this volume is equal to 28.88 centimeter cube divided by 2.39 into 10 raised to minus 23 centimeter cube divided by unit cell. That is equal to 12.08 into 10 raised to 23 unit cells. Since each BCC unit cell contains 2 atoms, therefore the total number of atoms in 208 gram is equal to 2 into atoms divided by unit cell into 12.08 into 10 raised to 23 unit cells. That is equal to 24.16 into 10 raised to 23 atoms. So let's move to the next question. That is, X-ray diffraction studies show that copper crystallizes in an FCC unit cell with a cell edge of 3.608 into 10 raised to minus 8 centimeter. In a separate experiment, copper is determined to have a density of 8.92 gram per centimeter cube. Then calculate the atomic mass of copper. Well, in case of FCC lattice, the number of atoms per unit cell Z is equal to 4 atoms. Therefore, capital M is equal to D into Na into A cube divided by Z. Substituting the values, we get 8.92 gram centimeter raised to minus 3 into 6.022 into 10 raised to 23 atoms mole raised to minus 1 into 3.608 into 10 raised to minus 8 centimeter the whole cube divided by 4 atoms. That is equal to 63.1 gram per mole. Thus we can say that the atomic mass of copper is equal to 63.1 unit. Moving to the third question, that is, silver forms CCP lattice and X-ray studies of its crystals show that edge length of its unit cell is 408.6 picometer. Then calculate the density of silver. Well, the atomic mass of silver is equal to 107.9 unit. Do you have any idea about the answer? Well, let's discuss. Here, the lattice is CCP. Then, the number of silver atoms per unit cell Z is equal to 4. And molar mass of silver is equal to 107.9 gram mole raised to minus 1. That is equal to 107.9 into 10 raised to minus 3 kilogram mole raised to minus 1. Edge length of unit cell A is equal to 408.6 picometer. That is equal to 408.6 into 10 raised to minus 12 meter. Well, as we know, density D is equal to Zm divided by A cube into Na. Substituting the values, we get 4 into 107.9 into 10 raised to minus 3 kilogram mole raised to minus 1 divided by 408.6 into 10 raised to minus 12 meter the whole cube into 6.022 into 10 raised to 23 mole raised to minus 1. That is equal to 10.5 into 10 raised to 3 kilogram meter raised to minus 3. That is equal to 10.5 gram centimeter cube.